Hello, I'm Doug, and this is a talk I gave at Boston Bar Camp in April 2010. A bar camp is self-organized, and people talk about what they feel like talking, and people show up if they are interested. So I put up this suggestion, a unified field theory, on one t-shirt, where I was going to explain it, hopefully in an hour's long period of time. And as you can see, I got a check mark. A lot of other things had multiple check marks, but that's the nice thing about bar camp, is one check mark is enough. And so I gave this at 4 o'clock, and about 16 people or so were there at the start. We had about 8 people last through the, I don't know, maybe 50 minutes or so. And 4 of those actually bought shirts on the day, which was in fact the target I had for sales. So very satisfied. It was a lot of fun chatting with the folks. And so these are the slides I did for them, and I'm just going to repeat them right here. So there are many steps to understanding this t-shirt. The first step that one must take is to understand what Quaternion and hypercomplex products are. And I'm pretty sure most people listening to this video won't know what a quaternion or hypercomplex number is, but I will go into the details about that. Shortly, it's numbers that have 4 individual parts to them, and they can be multiplied by each other. Then there is something called a gauge, which is a very sophisticated idea that you usually only get to in graduate school in physics. But I'm going to try and explain it enough so you can see that, well, those things cancel out, and so there's no need for the Higgs boson. Oh, let me guess, you don't know that either. That's okay. That's a very important undiscovered particle in physics, and I'm thinking the reason it's undiscovered is that it's not needed. The third task is to get a sense of what symmetries are in physics and how that leads to charges in physics. And there are only 4 fundamental symmetries and 4 fundamental charges, and we should be able to spot them somewhere on the t-shirt. And then we will derive the field equations which are on the front based on the mathematics that happens to be on the back. Now, what's shown here is actually the very front of the t-shirt, which actually is in black and white, and the back of the t-shirt, which is also black and white, but I made this poster up so that you could use the colors to see the connection between what is written on the front versus what's written on the back. So what does it say on the front? It says, the stand-up physicist, that's me, said, a math equation, basically, 0 equals del squared phi equals the second time derivative of ai minus the second xj derivative of ai minus the second xk derivative with respect to ai, okay? And there was light, gravity, radiation, and a nucleus, but no stinking Higgs. This is, you might say, the next step in fundamental t-shirt design from the one that says, and God said, and it has the Maxwell equations, and there was light, because that only explains how light works. The front of this t-shirt claims to do the other 3 forces of nature in a way that doesn't need this Higgs particle. The Higgs particle is something physicists are working very hard to discover at the Large Hadron Collider. They're spending $10 billion to spot it. And this t-shirt says we don't need it. That is the claim. The way I back it up is with all the scary math on the back. If it is in yellow, or a little bit off yellow, I guess there, it has to do with light. The lowest chunks of yellow are the symmetries that involved with light. A normalized complex number is symmetry U1. And the Maxwell equations can actually be derived from that funky L thing, which stands for Lagrangian. The yellow parts of that actually lead right to the Maxwell equations, as long as you subtract the gauge term, because as written, those actually are gauge dependent, the del phi thing is. And so to make a gauge independent, you had to subtract del phi star. But if you do that, then you can get directly to Ampere's law and Gauss's law. And the stuff in purple is supposed to somehow be related to gravity, because it all uses the hypercomplex product. That, briefly, is a type of multiplication that doesn't have any minus signs. It's all positive, it's all sunny, it's all warm, and because of that, it only knows how to do the attractive force of gravity. The stuff in green is supposed to be related to the symmetry found in the group SU2, and that has to do with the weak force. And then we've got two things that are awfully darn similar, except there's a little star in there, and that symmetry is called SU3 and has to do with nucleus. So the shirt is in black and white. The poster is multicolored. It would just be considerably more expensive to print out that one. So anyway, that's the kind of overview of the t-shirt, and how we're going to spend most of the time with the back of the t-shirt, actually, trying to understand these kinds of issues. So quaternion products are mashup of scalars and vectors and complex numbers. So actually, let's take a step back from that even further. What is a scalar? A scalar is just like a number that you use every day. That's 3 apples, okay? But a vector is a number that you also use every day, but it's got a pointiness to it. It's that much to the right. It's this many units up. It's that much near or far. And in space, there are really usually 3 directions you can go to. And what mathematicians did, specifically this guy named Gibbs, was he separated scalars from 3 vectors because people thought that would be easier to understand. They were actually born in something known as a quaternion, where those were like always together. And so I'm being kind of retro here, and I'm going back to where scalars and vectors were born and saying, I'm never letting those 2 part ways, okay? So people are like, well, why be so retro? I mean, it's got to be really, really tough to work that way. And it's like, no. It's like, what are all the possible ways you can multiply a scalar and a vector together? And if you have some experience with scalars and vectors, there are not that many possibilities. As a matter of fact, here's the complete list. You could take the scalar and multiply it by the other scalar. That's the S prime. You can form the dot product of V and V prime, and that shows like how much in the same direction they're both going. Now that does have a minus sign, but that's because of this kind of complex number flavor that is involved with quaternions, and that's it. I mean, it's not that big a deal to remember, oh yeah, kind of complex number, like I guess I'll throw a minus sign in there. But actually, that's actually one of the deeper wonderful things about quaternions is that if you just learn complex numbers, they say, oh, we'll draw it on a piece of graph paper and we'll tell you the difference between real and complex numbers is rotating the paper by 90 degrees. That feels kind of empty to me. And here it's no. I'm dealing with time sorts of things, which are real scalars. I mean, there's just a number associated with it, versus things that I can point to. And pointy things, those are the imaginary numbers, and apparently there are 3. And there are 3 dimensions of space. Wow, was that chance? I don't think so. All right, so then we take this scalar and we can multiply it by a vector, and we just get another vector. It'll either be longer or shorter, depending on whether s is greater than 1 or less than 1. And then you can also have these cross products, which if you've had them in high school, you had to struggle to remember which one is positive and which one is negative, because they definitely have a very set pattern out there, and you got to learn that. And I still had to, look at my fingers and go, which one is positive, which one is negative? Oh, well, that's the way it goes. Now, what I do is use hypercomplex numbers also. But these things are used by like almost nobody, except this one guy named Clyde Davenport. He's kind of a fellow like me who's like, wow, this is really cool and nobody likes it. Oh, well, maybe we'll find a good use for it. And this one, again, is easy because it's just like quaternions, except there are no minus signs. I call this the California representation of hypercomplex numbers because it's all sunshine, it's all positive. And so you notice that it looks pretty darn similar. Okay, I don't have that complex number sign switch in there. I still got the scalars multiplying by each other. I still have vectors getting longer or not, depending on whether s is greater than 1 or not. And, well, now I've got this circle x. And, I should say the box x and the circle x are not part of anybody's symbol system for writing numbers. I'm very uncomfortable that I had to say, I need these so badly, I'm going to use them. Because that means that it breaks down lines of communications with professionally trained folks. But hypercomplex numbers are just so little used. And yet you can see that the starting ingredients were exactly the same. And a lot of the resulting things are the same. So there is this overlap, and I just thought the box X and the circle X kind of look really symmetric, and they're part of this, hey, don't allow any minus signs in here. But that creates a problem. And the problem is hypercomplex products are just too positive. So to get around that, I'm going to use a conjugate operator, and that's going to flip the sign of that V prime in there. And in that way, I'll end up with the same exact scalar as quaternions. And this is important particularly to physicists because that particular scalar is invariant under a gauge transformation. Very fancy wording there, but it's kind of Euclid's old hypothesis about triangles, about a squared plus b squared plus c squared. That's great for space, but if you do space-time, then you actually need this thing where you've got a sign flip between the space part and the time part. So whenever I use a hypercomplex product, to be relevant in physics, I'm always going to conjugate something. So that's my ground rule, so that I end up with exactly the same scalar every single time. So now we go into the issue of gauge. And we talk about actions are let's see. Actions are integrations of Lagrangians. Did that help? No. Okay. Let me take a step further back. Lagrangians are every way energy can be exchanged in a unit volume. And then if you integrate that over all of space and time, then you get back energy times an amount of time. That is called the action, okay? And what you do with the action is actually look for something that you can vary and not change the resulting action. So, one of the things we look for is gauge invariance. In other words, can I change the gauge, and if I do, does it have an effect on what's going on in the action? And if you've got something that is invariant under this gauge transformation, it means something. It means that the particles are traveling at the speed of light c, that there is no scalar field, and I'm free to choose things like d phi dt or the divergence of A. So if an action is not invariant under a gauge transformation, it means that we're traveling at less than the speed of light. It means there's a scalar field around somewhere. And that these terms that are part of the gauge, this d phi dt and the divergence of A, those are fixed by conditions. All right, good. So the weird thing is that photons and massive charged particles interact all over the place. Photons, of course, are traveling at the speed of light. And massive particles, they're not. So you have to have field equations that have both these properties. You somehow have to be able to say, oh yeah, I see how that's invariant under gauge transformation, because the photons are going to be able to do all that work, and I've got massive particles. So I can't have that. So how do we do that today? Well, the current answer is the false vacuum of the Higgs field. So there's something called the standard model, and it has the symmetries U1, SU2, and SU3, which correspond to 3 of the 4 known forces. That would be electromagnetism, the weak force, and the strong force. And this works great so long as nobody has a mass. But that clearly is not the way it really is. So this scalar Higgs field actually does grant these particles mass by using this Mexican hat trick. And the trick is that the vacuum state, it's a false vacuum. And since it's false, there is spontaneously symmetry breaking down to the brim of the hat, the base part of there. And that's where it really hangs out. But that process of breaking the symmetry spontaneously is what gives it mass. And we've been looking for the Higgs particle at least since the 70s, and just every decade the search gets more and more serious, because we really need that for the standard model to work as people think it does these days. And there's this huge experiment going on called the Large Hadron Collider, LHC. It's a $10 billion bet, and one of its huge jobs is to find the Higgs. Its other job is actually to find a bunch of superparticles, and the reason we need superparticles is because that way we can get gravity along with these 3 forces. And the wonderful thing about the t-shirt is that if the math on the t-shirt is near the right answer, as I like to say, if I'm barking near the right tree, that's my phrase, then we don't need the Higgs, and we also don't need any super symmetry. So it'd be a very unpopular shirt at LHC. So what we're going to do now is form very simple quaternion products. We're just going to take a differential operator and a potential, and it just amazes me that we're going to end up with the fields of electromagnetism. Okay, so this is div grad curl and 2 time derivatives. And the nice thing about using quaternions is you understand what the heck is going on here. You have a potential in space-time. So it's in space-time, it should have 4 parts. And you say, I want to understand every conceivable way it can change in time and in space. Well, that sounds like you're going to get a very complete answer, doesn't it? You should be able to count like about 16 little pieces out there that go into it. And if you look at that line there, you can actually count them all. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, I counted 16 little parts in that second line there. And the definition that everybody uses for an electric field is minus dA dt minus del phi, so we happen to have minus E. And the definition of the B field is just the curl of A. And this scalar part is actually a gauge field. And I have another video actually where I say this whole thing transforms like a rank 2 tensor, because it does, which is a fancy way of saying I've got 2 quaternions here, each of them transforms like a vector, and now I'm going to multiply them 2 together, so I transform like a rank 2 tensor. And that happens because this is a quaternion operator. All right. So I'm going to repeat this exercise, but with hypercomplex products. And I'm going to claim here that these have to do with gravity fields. Why do I feel that way? Well, because gravity is the universal love force. And I mean that in a purely technical way. I must admit, I love you. Okay? And I don't care what you're made of. I don't care if you're alive or dead or a fish. I actually most love things that are close to me. It's just the nature of gravity. It's one-sided in its affection for absolutely everything out there. That's standard physics, put in non-standard lingo, okay? But the question then becomes, how can you be so one-sided in your affection? How do you make your accounting system be such that it doesn't have an idea how to hate? And my suggestion is it's the hypercomplex product, okay? So now let's see what happens. Remember, I do have to throw some minus signs in there somehow, so that's where the conjugate guy is coming in there. And when you do this sort of exercise, you get exactly the same gauge term, all right? But we have the dA dt and del phi terms having different signs, and that matters. And then we've got something that's like the B field, except that it's got that circle across, because all those signs have the same sign. I guess since we've got a minus sign, everybody's minus there, but so we get a minus small b. And that will not be the same as the big magnetic field B. Now, it's kind of made of the same stuff, but sign changes are very important. So now we do something that's actually written on the t-shirt itself. What's written on the t-shirt is the del phi phi del thing, and the bottom line, the del box phi star box del star box phi star. That's not easy to say quickly. All right. So why are we doing this? Because Lagrangian seems to love the squares of things. Squares of things show up time and times again, and we're squaring rank 2 tensors. if you want to put it in those ways. But when you do this, as I've written, you get a G squared term. So that means that that particular form is gauge dependent, and we remember that means it applies to particles that have mass, and we've got this E squared and we've got this B squared. And when we do the corresponding thing with hypercomplex multiplication, again we get a G squared, exactly the same gauge field squared, and an E squared and a minus B squared. So if we subtract one of those from the other, which is what happens on the t-shirt, overall it's going to be gauge invariant. It won't care because I subtracted G squared from G squared, leaving we 0. Okay? So we'll have the E squared fields for electricity, and what I'm speculating is for gravity, and we'll have the B squared field for electromagnetism and the corresponding symmetric B for gravity, but there will be no gauge. And so that's why we don't need no stinking Higgs. Separately, it's gauge dependent, and then when you put it together right, it's gauge independent, so those forces can be mediated by massless particles like the graviton, the photon, and the gluon. So now we're going to look at symmetries in the Lagrangian, because symmetries in a Lagrangian means there is a conserved charge. So the idea is that we vary something in the Lagrangian, we integrate that over space and time, and if we go out, say, 1 second from now, it'll have some value, and if we go out 100 seconds from now, just varying that thing, we'll get the same kind of result. All right? So let's look at some examples. If we were to vary time, there is no t sitting by itself in the Lagrangian written on the t-shirt, and so therefore energy is conserved. Similarly, there is no like position dependence. There is no x written there explicitly, and so that means that linear momentum is conserved. And finally, if we kind of play with angles and whatnot, won't change a thing in the action, and so angular momentum is conserved. So now we're going to look for other symmetries that are in the t-shirt, and I've written them as one of them as a over the absolute value of a. That is what's known as a unit complex number, a unit circle in the complex plane, the symmetry group U1, and it only has one element in its Lie algebra, and it basically has corresponds to electric charge. It's a bit of a jump, I admit, to going, well, I've got symmetry and I've got electricity. But that's kind of the math logic that's there, that physicists talk about. And, you know, it's still one of those things that, you know, you can go, yeah, but why does that feel like a shock when I, you know, rub my feet on the carpet? I can't answer that. I can say that the math is such that if there's a symmetry like a U1 symmetry, that is the same as saying, oh, I bet you're going to conserve electric charge. All right? So then there is a symmetry SU2, which is also known as a unit quaternion. So since I'm using quaternions, of course I can do SU2 symmetry, and that I do as the exponential of a minus a star. Now, there are other ways that this group can be represented, okay? It's just that if I'm using quaternions, this happens to be an easy one to write out. And there are 3 weak charges. And so, we can get that correspondence between the two. What's a little bit more radical is my suggestion about the group SU3, which has 8 generators in its Lie algebra, and saying, hey people, just take these normalized quaternions and an exponential and take the conjugate of one and multiply it by another. The reason you have to do the conjugate is because without that you have what's called electroweak symmetry, and if you got one thing that's got electroweak symmetry and multiply by another one, you're going to end up with a third one that has electroweak symmetry. You have to have symmetry that's somehow different, and so that's what the star is doing. All right, but why 3? Why these 3? What are you, 5? That's just a little joke, because it's like when you're doing unified field theory, believe me, you can keep on wondering why something works, and you'll reach the boundary of what you know pretty quickly, actually. As I say, this is not actually relevant to the T-shirt, but I really think it's too mind-bending. It really is kind of cool. So it starts with a very smart Frenchman, René Descartes. He developed pictures of math using analytic geometry. And to me, this is, right near the absolute top of important discoveries in the history of mathematics. Because now you can take some polynomial expression, which I wouldn't have any sense of what the heck it meant, and just chart it. Why not? Yeah, thank you, Renee. Now I got a sense of, it's going to go way down negative, which makes sense when I think about it. And it'll go on into the infinite positive kind of region, and there'll be some point where it crosses the x-axis and the y-axis. I mean, that all kind of makes, I can wrap my head around it in ways that, if I just had that polynomial, I'd be kind of lost. All right. So I think the direction physics will go eventually is to develop analytical animations using quaternions and hypercomplex numbers now. But that every expression in a graduate level quantum field theory book will necessarily have an animation related to it. That's exactly the same expression, and that would be just wild, in 50 or 70 or 100 years, to see the new books on quantum field theory and get pictures of everything, moving pictures at that, of everything they've got in the book. I mean, that's quite the big dream. So how do I do this at the current time? Well, this is software I've written. And so the idea is that you make many events randomly in a straight line, do some math, sort by time, and just animate. And when I say just, this is my software, I don't think you'll be able to read it, but it's just supposed to be creating a bunch of random numbers by typing out some text, and then you can actually pipe the results into another function. And there are a lot of different functions, okay? And you can actually take these things and sort them by their time, okay? And I think that's where I sorted it by time. And then you can actually say, okay, what I want to do now is get a graph of that. And so you just write the program QGraph and say, go ahead and start plotting away. And so it does. And so we can now visualize U1 symmetry, the symmetry of electromagnetism, the unit circle in the complex plane. Now, what I found when I started doing this was that animations by themselves made no sense. My brain just can't think about animations effectively, at all. So what do you do about that? Well, I surrounded by a bunch of things that don't move very much, and that would be the complex planes. and those planes are for y and time, z and time, and x and time. And when you look at those and the animations together, it kind of makes some sense. So it flies apart quickly, and then it slows down and stops, and then comes together, and the kiss of death, and it's gone. I also put up all states. So when you look at all states, it's like, wow, that's as straight a line as could possibly be. But that's because it's straight in space, okay? And the circleness has to do with the relationship between space and time. And because I'm also thinking about quantum mechanics whenever I do this, there's an idea in quantum mechanics about being the superposition of all possible states. Well, that's what the all states thing is. But then when you go and actually make a measurement, well, then you're going to see like a pair of these sorts of things. So I think the panels on the right-hand side may be a kind of new visualization approach to quantum mechanics. That's the big dream. All right, but people kind of knew about this unit circle thing. But when you bring up the visualizing the weak force, you're not going to get anything but possibly what I'm claiming here. Okay, the idea is, there's that exponential a minus a star. And so what I did was I took, 10,000 random quaternions, just plugged them in there, and this is the animation I got. This is kind of crazy. It starts out at 8 separate points that grow into each other, form a ball, and then collapse into nothing. Okay? And that just mathematically is the animation you get from that. I find it's often useful to actually watch the shadow in the animation box. Let's see it. Yeah, you can see how you can see how it starts with these points and then forms circles and then a sphere and then goes away. And there's no other person I can tell who actually thinks that the group SU2 has a visualization. But of course, we can take the results of the first one, the U1, and multiply it quite literally by SU2, and then you get this bias towards the past thing. It's a sphere. It just doesn't like the future as much as it does the past. And then we've got the SU3 thing, and this is a uniform ball. How nice. Finally get something uniform by getting out to SU3, conscious of the fact that we've already got a U1 and SU2 inside of both of those. And this is a little bit about gravity, the idea that if you're located in a different place and there's a strong gravity field around, your notion of one is not going to be the same as my notion of one. Okay, so why these three? All right, because we're looking at the symmetries of 1, 0, 0, 0 in space-time. And when you do that using quaternions, you use U1, SU2, and SU3 to describe a uniform unit sphere. And there's kind of like nothing more you can say. I mean, you've got your unit sphere. You're done. The observer is at 0, 0, 0, 0. He sees something, so he's got to put that on a sphere. Might as well put it on 1, 0, 0, 0. And we've got these symmetry groups. We've got those symmetry groups. Therefore, we have conserved charges. One that's got one element to it, that would be electric charge. Another one that's got 3, that would be SU2. And one that has 8, SU3, the gluons. I am the only one who says anything at all like it, like this way. Okay, so don't like go to your professor and say, "Oh, son, I was wondering about quaternions and SU2." You're they aren't going to be chatting away with you if you bring that up. All right. So we're actually now going to move on to trying to get to the Lagrange density, and that's on the back of the. how do I say this? So we're going to try to teach you something that really only shows up in graduate school in physics, and it usually only happens in one course, one that has what it was the Goldstein book, or if you have Landau and Lifshitz, and it's kind of used in that one course, and like nobody ever really goes back to it. They say, oh yeah, that's totally fundamental, but they just don't use it on a day-to-day basis. So but I'm going to try and give you a sense of what it's about. And the calculus that you need is some of the first stuff that you ever learn, and that is like if you have x squared and you take the derivative of that, you get 2x. I threw in a half in there, so 1/2 x squared, the derivative of x squared with respect to x, is just x. I think that was the first one I learned. Take that 2 down and subtract 1 from 2. That ends up with 1. And if you got a half in front of there, you just end up with x. And another easy one is xy with respect to x just gives you y. Okay? Now, what's kind of difficult about the Euler-Lagrange is that x is much more complicated. Okay? It's like d phi dt or dAx dy. Okay? But just consider that to be actually x, and don't get scared. But as I say, you've lasted this far, so let's see if we can get through it. So what we have to do is square these fields. And I was thinking, am I really going to try and show this to anybody? That sounds insane. But that's the nice thing about squaring things, is you really don't have to pay too much attention to signs. You go, oh, it's going to square, so it's going to be, it makes it so much easier. Okay? So let us go ahead and square the e squared part, so that would be the minus dA dt and minus del phi. And you go, okay, so I've got 3 dA dt's, I got 3 del phi's. I'm going to have the squares of each one of those, and that's that first line. And since they're squares, everybody's positive. Okay? And so that's not a hard collection of 6 to come up with. And then you go, well, we've got some cross terms. And the only question with cross terms is whether they're going to be positive or negative. And what that depends on is whether those two terms have the same sign or different signs. Well, they have the same sign, so they're going to have the same sign as all the square terms. Okay, so we got a 2 there, and then we've got these 3 different cross terms. Now, how about the curl of A, squaring that? And that's, of course, where I got most scared, because I have trouble figuring out what the curl of A is, let alone figuring out what 2 of those are, and then squaring them. And I was like, oh man, this is going to be super bad. And then it was like, no, this is just going to be like the first one I did, okay? And so I don't have to think about which one goes to which. I'm going to get the complete set of squares. And because there's a minus sign, the complete set of squares is going to be negative. So you go, oh, that doesn't look so bad, that third line there. It's like, think of all the different AXs, AYs, and AZs, and they're all squared. There they all are. Of course, then my deeper fear was the cross terms. It's like, no. It's the same kind of business going on here. Now, in the curl of A, they have opposite signs. So this cross term thing must have the opposite sign of the squared terms. Okay, good. I don't have to worry about signs on that anymore. All right, and it's like, and what are those terms? And that's, it's like, oh, it's really Mr. Mix and Match here to get these 3 terms. And so squaring the E squared and B squared was not as bad as I had feared. now we have to repeat this exercise, but for that small e and small b sort of thing. And, oh, actually, let's see that again. That looked pretty subtle. Yeah, we had the cross terms were plus here, plus, and so it goes plus, plus, minus, plus. And now we go plus, minus, minus, minus. That's it. It's like, sweet. It's like, why was that? And it was like that because, again, we were dealing with squares. So really the square terms couldn't change at all. All right? It's just that now the E field has a difference in sign between those two terms. So that's got to be, those cross terms have to be the opposite of what the squared were. And for the B field, oh, that's right, it's got to be the same sign as the square thing, so that's why it's minus. All right, so that is nice. And now we say, well, but my Lagrangian had both of those together, actually one minus the other. So, oh, look at that. They all the cross terms go away. I mean, that is really nice. And we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms in all. How nice. Actually, it's more than nice. I mean, if you go through that much math and you simplify things, you're probably doing something deeply right. Okay? So that is the Lagrangian. And now to get to the field equations, you need to apply the Euler-Lagrange equation. And this thing looks darn scary. I mean, what does all these mu's and phis, all kinds of mean? And it's, as I explained it, it really is a cross between a Sudoku puzzle. Oh, not Space Invaders. That's not spelled correctly. Missile Command. It should be Missile Command and Sudoku. Okay, so here I've written this out by hand, and if you get serious about this topic, I highly recommend doing this by hand because it's just fun when you finally get all the signs right. And it's okay to borrow my notes and just go from there. And we're going to actually get to the Maxwell source equations in this exercise. It's very similar for the unified field theory. So you can see that what we do with this Lagrangian is we're now going to take derivatives with respect to d phi 1, or del 1 phi, del 2 phi, and del 3 phi. And you can see where they actually end up. And you'll actually also take a derivative with respect to phi itself. And that pulls down this charge density. And that is how you derive the Gauss's law, 1 of 4 of Maxwell's equations. And I highly recommend that you do this actually for another reason. Because if you do this, and you leave this paper casually on your desk, then people will presume you are the smartest person they know. It's a great party trick. Anyway, so now we go and we take the derivative with respect to A1, and you can see these things landing in all kinds of different places, as well as taking a derivative with respect to A1, and boom, that's where they all go. And boom, this is what happens when you work with A2 and all the derivatives of A2. They go to all these different spots here. And I underlined here to make it a little bit easier to see which ones have to do with electricity, that would be in blue, and which ones have to do with magnetism, they are in red. And boom, to get the third component of Ampere's law. And there it is in all its glory. The real, if this was Missile Command, you'd be in a lot of trouble here. And that is how you actually get the Maxwell source equations. And I actually have another video devoted just to that subject and go into it in a little bit more detail. All right. So if you spend the $18 going to, I don't even list it here, bit.ly/capital G, capital E, capital M, lowercase t-shirt. If you go there, for $18 you can get this t-shirt without the color. Sorry, that it's just the black and white. But you can see where those claims on the front are coming from. Just to quickly review, gravity is because we've got the hypercomplex product. It's all sunshine, it's all positive, and that's why it only knows love. But you do have to throw in a little negativity in there so that you can get gauge canceling going on. And because you're doing gauge canceling there, you don't need the false vacuum, the Mexican hat trick of the standard model. You don't need no stinking Higgs. The the SU2 symmetry is this exponential business. The SU3 thing is when you bring two of these together, as long as you throw in a star. And so the reason this is potentially cool, all my work depends on me barking near the right kind of math. But if this is near the right kind of math, what's cool about this is it's kind of like you could wear it before this has appeared in a peer review publication, because I've had some trouble getting it a peer review publication because nobody works with Quaternions. I shouldn't say nobody, nearly nobody, and it's almost absolutely nobody works with hypercomplex products. Maybe a short story about how, yes, I have written up an official sort of publication. I've submitted it to a journal, and they said it's too radical because you use hypercomplex numbers, and nobody uses those, and a few people use Quaternions, but there's not much interest there. Send it to this more radical journal, and I did. And they said, wow, you're using Lagrangian. That's like so 18th century and boring. You're too conservative. So you can go out and buy this shirt and support it in that way. I know I wore it to a dance the other night and got into arguments with 3 or 4 physicists. Well, not arguments, but discussions, okay? And I danced with some of these people. So actually 2 of them. The 2 women I danced with, who I had got a discussion with this on. So it's fun shirt to wear, and let's just hope that somewhere the math here has a kernel of truth, because if it does, we will be seeing wonderful pictures of really difficult field theory in the future. Thank you very much.